lecturer who will give the Rothschild Lecture, Graeme Milton. Used to be my colleague at Courant, but now has been for many years at the University of Utah. And our topic today is metamaterials. Graeme, and you have a mic, I think, so.
Yes, I have a mic. I assume the mic is working. And anyway, it's great to be here. I just arrived on Friday, and nice to see some familiar faces, many familiar faces, but also new faces too, who I hope to get to know. So we're just talking about metamaterials, and so I thought I'd start with a very simple example. So if we just take a wine glass, it rings quite well. So that's the wine glass containing air. If we now fill it with a second material, which is water, and it still rings quite well. But now let's make a composite material of air and water, and the best way to do that is with something that bubbles, such as Alka-Seltzer. And I should just let it bubble for a little while. And then, so it changes completely the sound. And there's several effects coming on there, but there's some resonance with the small bubbles called the minora resonance, and basically it absorbs, the bubbly fluid absorbs sound, and that's been used with, say, submarines to sort of cloak the noise of the propeller. But metamaterials have been with us for a long time. Another old example, so this comes from the British Museum. If you haven't seen it before, this is the Lycurgus cut. And what's striking is that the glass in the cup takes completely different colors depending upon whether the light source is in front or behind. And that's due to the small metal particles inside the glass. It's small metal, nano-sized particles of silver and gold. The actual theory for that, it's the same as for stained glass windows too, to get in old churches, to get the beautiful reds. It's a composite of gold sphere and glass. It's not a chemical reaction at all, but rather it's a resonance caused by the interaction of electric fields with spheres. And so this is actually, appropriate because it's at Trinity College, Cambridge. And then the curious name here, J.C. Maxwell Garnett. And of course, we're all familiar with J.C. Maxwell. And so how did he end up with the name J.C. Maxwell Garnett? And the story is his father, William Garnett, was actually the first demonstrator for Maxwell here at Cambridge, and named his son, I guess he was so impressed that he named his son after Maxwell. And he didn't actually, he went on to become a barrister, but he was interested in a medium containing small metal spheres. There's a formula sort of associated with this. So this gives the effective dielectric constant as the mixture as a function of the dielectric constant of the air or vacuum and the dielectric constant epsilon 1 of the metal. And here F1 and F2 are the volume fractions of the two materials. F2 is actually 1 minus F1 here. This formula actually has sort of a long history too. Maxwell Garnett is listed because he's associated with this in formula in the optical regime where these constants are complex. And you notice there's a denominator here, and that suggests that this could be close to zero, and in which case you get a resonance, and that's really what's behind the colors of these glasses. It just goes back further. Faraday had a model for dielectric medium where he thought dielectric medium were actually consisting of metal globules surrounded in a background, and at that time they weren't aware of atoms and things like this, or the structure of atoms. And then Clausius and Mossotti sort of built upon this and derived an approximation formula. Mossotti, you'll notice the period here, 1846, that's when he first submitted his paper. 1850 was when it first got published, and you wonder about what happened in the gap there. What happened was he got tangled in a war. He had a battalion of students from the University of Pisa, and he got imprisoned, and it wasn't until he got it out that he was able to publish his paper. So there was a lot of debate about these different approximations. It was settled a little bit by Rayleigh, who noticed that it becomes exact in the dilute limit of a periodic array of spheres. And there's a nice historical article here if you're interested. Later it was realized that this is actually an exact formula. Here it's for conductivity, but it's exactly the same for the dielectric constant. Compare that formula up the top with this formula here. And the key realization, this was Hashinen and Strickman in 1962, although the idea is due to Hashinen for elasticity in a slightly earlier paper. The idea is that if you've got a core of conductivity sigma 1, a shell of conductivity sigma 2, there exists an appropriate value for sigma naught where the current in the surrounding material is undisturbed. And so this is actually sort of an inclusion that's actually invisible to a uniform field. And if you've got one inclusion like that that's invisible to a uniform field, you can add another one and so on, fill up all space with these coded inclusions. And at each stage, the average properties are determined by sigma naught, and that doesn't change. And that appropriate value of sigma naught, which gives you the neutral inclusions, is given by this formula. That's a straightforward calculation. So, and then this is sort of more recent, in 2002. This is an experiment of Naomi Hallis's group. Instead of considering metal spheres, Naomi had a hollow gold, or nanoshells actually, sort of. And so this is the red color you get from solid gold spheres in liquid. But as you carve out a hole inside each of those spheres, you get a whole array of different colors ranging to the infrared here. And the infrared ones are of quite some interest. They look invisible, but Naomi's group proposed them as a method for treating cancer, because they could absorb infrared radiation and heat up and kill cancerous cells that were nearby. And then a model for this might be this sort of doubly coated sphere assemblage of Schulgasser. And again, there's a simple formula for its conductivity. It's just an iteration of the one before. So the upshot here is that the properties really depend upon the structure. And you could ask about, well, what about model independent bounds that are independent of the geometry? And so back in 1980, myself and David Bergman obtained these bounds, which are sort of circular arcs in the complex plane, depending upon what you know about your material. And so epsilon 1 and epsilon 2 are the dielectric constants of the two materials. If you don't know anything about the material, then a diagonal element of the dielectric tensor necessarily relies in this large region omega, and this straight line just corresponds to a laminate of the two materials with the layers in the direction of the applied field, and this is a laminate with the layers perpendicular to the direction of the applied field. And then other geometries, if you know the volume fraction, you can restrict the region down to this one here. And then these two are associated with assemblages of not coated spheres, but doubly coated, not coated spheres, but coated ellipsoids. And in 2 dimensions, if you know the material is isotropic, you can narrow it down even further. And the geometries on both sides of this are the doubly coated spheres. In 3 dimensions, the picture is not yet complete, believe it or not. Anyway, but now, of course, we've got unprecedented ability to sort of build novel structures. This is sort of an example of the group of Martin Wegener. We'll come back to this later. And here's another one of the group of Julia Greer. This is all sort of different microstructures. So basically, within limits, a lot of things that you thought may have been impossible are now possible to actually make. So what are metamaterials? So the original definition goes back to Walser in 1999, and it's quite a mouthful. They're macroscopic composites having a man-made 3-dimensional periodic cellular architecture designed to produce an optimized combination, not available in nature, of 2 or more responses to a specific excitation. So anyway, the word caught on, but the definition didn't. I think people think this is a much too narrow definition to what people mean by metamaterials now. A simplified definition of Browning and Wolff in 2001, metamaterials are a new class of ordered composites that exhibit exceptional properties not readily observed in nature. That's good, but then it becomes a debate as to what does that mean by not readily observed. Okay, we have this definition. This is mainly actually Martin Wegener's definition, and that metamaterials are rationally designed composites made of tailored building blocks that are composed of 1 or more constituent bulk materials, and the metamaterials properties go beyond those of the ingredient materials qualitatively or quantitatively. And then, well, there are a lot of work has got into other sorts of classes of novel materials, periodic materials that have band structure, and so you can to eliminate those classes of materials, you can add the addendum that the properties of the material can be mapped onto effective medium parameters. So it's actually a surprise to find the properties that composite can exhibit. So here I want to talk about one example. This is called the Hall effect, that if you take a copper sheet and if you run current from one end to the other, and you impose a magnetic field perpendicular to the plate, then the electrons moving from one side to the other are feeling a force perpendicular to both the velocity and the magnetic field. And so that force then acts orthogonal to the plate, and or in a transverse direction, I should say. And the charge builds up on one side or the other, and you develop a Hall voltage until you reach the point where this force here is balanced by the transverse electric field, the force on the electrons due to the transverse electric field. This simple argument tells you that the sign of the Hall voltage tells you the sign of the charge carrier. And that's sort of interesting. That's called the Hall effect. Hall had realized this even before the electron was discovered. And if you take a cell phone or something like that and you use it to detect the direction of north, what's going on is inside your cell phone, it's using the Hall effect to do that. And so, so that's in elementary physics textbooks, you hear this, that the sign of the Hall coefficient tells one the sign of the charge carrier. But that's based on a very simple picture that the electrons travel in straight lines. And if you've got some microstructure, that's not necessarily true. And So there's actually a counterexample, and from a math perspective, it amounts to find a conducting periodic composite with, say, cubic symmetry, where the matrix-valued electric field, this is an idea of Luc Tartar, is that you should look at the electric field corresponding to 3 directions of the applied field, and that actually gives you then a matrix-valued electric field, 3 by 3 matrix-valued field. And if you can find that it has a negative trace of its cofactor matrix in some regions, then you're done by perturbation theory. And this is the geometry which we were. This is with Marc Brion. But it was sort of an interesting story is that Marc and myself were interested first in the 2-dimensional geometry, and the 2-dimensional geometry looked like medieval armor, like chainmail. And we saw this website of this guy, Dylan White, and wrote to him asking, can we use his image of this, it was a Japanese tile chainmail. It was exactly the thing that we're thinking of. And then he said, did you think about the 3-dimensional geometry? And that was precisely what we needed. And it was a 3-dimensional geometry of interlocking rings. Here, this is a photo of 2 layers. That's an actual photograph of rings built up by Dylan White. And in 3 dimensions, the geometry looks like this. And the cofactor matrix changes sign in the gaps here. And so this is where you put your material with a high positive Hall coefficient. And so that was a bit difficult to build. So the group of Martin Wegner actually found out a simplified geometry. You've still got the interlocking rings, but they're linked by a conducting bridge. And so now everything is just built from one phase, and that phase could be a semiconductor. And then, sure enough, one actually sees this sort of reversal of the Hall voltage. And what's really remarkable is that Martin Wegner's group actually went ahead and built this. And so this is using a 3-dimensional lithography technique. So here you've got this sort of interlocking ring structure. They built it, they tested it, and verified that it actually had opposite Hall coefficient. And I went to their lab and I asked, could I see this? And I was expecting something reasonable, but it's actually about the size of the whisker on your chin, maybe after you've had a shave. And it's really quite tiny, but it was enough to demonstrate the effect. Mention that's not the only structure which has this. This is an alternative structure of Christian Kern. Of course, if you've got the Hall effect, the easiest way of reversing the Hall effect is to switch the leads in the battery. In other words, if we sort of go back, so when you measure the Hall voltage, you connect a wire here to a wire there and a voltmeter across them, right? If you cross those wires in between, you would get a Hall voltage of the wrong sign. Well, that's sort of trivial. It's not really a Hall voltage that you're measuring any longer. But the question is can you do that sort of reversal at the microscale? And that's what this structure here does. It looks like this is a unit cell. It's periodically repeated. But you can sort of see, so current goes along here. Suppose there's a magnetic field from above, current's going along here, you get a Hall voltage across there. But if you follow this wire around, it then loops back and comes out there. So it's an opposite size. And this has cubic symmetry, that's why it works. And more detail, again, you can calculate the trace of the cofactor matrix, and everything checks out. This hasn't been tested experimentally yet. So another example, which is sort of curious, is negative expansion from positive expansion. You can combine materials, each of which expand when heated, to get a composite which contracts with heated. That sounds a little bit contradictory, but think of this here. Suppose the black horseshoes are rigid material which don't expand much when heated, and the grey coloured region here, suppose that's some material like rubber which expands a lot when heated. Then what's going to happen when you heat this up, the rubber's going to expand, this doesn't leave, and because the rubber's expanding, the distance between there and there decreases, and so the entire length from here to here decreases, and of course this idea you can build into a 2 or 3 dimensional composite. But that's just to give the sort of idea. The original designs were a bit more complicated of Lake, Sigmund and Tokado. I'll show the Sigmund and Tokado compared their microstructure with rigorous bounds that had been derived by Gubianski and Tokado. They were given by these curves here. And you can see what's the geometries which actually sort of come close to realizing these bounds. In particular, this is geometries which have negative thermal expansion, actually. And so if you like, there's a metamaterial mantra. What is not obviously forbidden may actually be possible, and is therefore sort of worthwhile trying to investigate this. So there was a lot of work, and Bob Cohn, Greg Allaire are some of the key players on bounds on composite materials in the early 80s and up to the beginning of the 90s. And it's a difficult problem, actually, so I won't say more about this at this point, but I'll just mention that okay, negative thermal expansion is maybe not so interesting, because you can have materials like ice. When you cool them down, ice expands. It has a negative thermal expansion. But what's more interesting is poroelasticity. It's the same equation but different physics. So poroelasticity, here you have fluid in the surrounding material. The pressure in the surrounding fluid plays the role of temperature in thermal expansion. And okay, so you needed a different phase here. You can have these chambers here are closed, and you can have a different pressure in those. And it's sort of quite remarkable that Martin Wegner's group was actually sort of able to make this, and in particular make the closed chambers. I think that even surprised them. It turned out that there was sort of, when they were building this with the 3D laser printing, there were micro cracks, and the micro cracks allowed the fluid to go out and leave the chambers behind. But let me show you let's see. So this is the experiment of whoops. Maybe it's don't know why I've got 2 slides, but anyway. Whoops. Let's hope. Oh, it's sort of odd. I don't. Do you know how to get rid of that? Not that movie. It's the other one. No, not that one. No. That one.
Which one do you want?
This one. except I don't want next slide. Okay, that'll do. I think that's enough to sort of see it. So this is the pressure here. So this is, if you like, this is a structure all underwater. If I had a balloon with air, an air-filled balloon, I put it underwater, and if I increase the pressure in the water, the balloon would shrink. This actually has the complete opposite behavior. You increase the pressure in the surrounding fluid, and the structure actually expands. And so that's, and then the side view shows basically the same. Oh. And that's there, okay, that's a bit more clearer. But anyway, that's, so the experiment works for that. So another interesting sort of metamaterial, new classes of elastic material, and this is joint work with Andrei Shukhaev in 1995. So this is we were looking for a structure which is a little bit like water, in that water only supports one loading, namely a hydrostatic loading, but we were after structures could support anisotropic loadings as well, for which the elasticity tensor is essentially a rank 1 tensor. And so this is a unit cell here. It's basically a diamond type structure where you have these double cone elements meeting at, with tips meeting at a junction here. We actually thought they'd never be made, but that's what the group of Martin Wegner did actually, and you can sort of see this sort of control parameter D. As this becomes smaller and smaller, it becomes more fluid-like. And you can also move the point P where the tips meet, and then you can get a structure which will support not a hydrostatic loading, but an anisotropic stress. And the key thing about this structure is that at any junction, only 4 tips meet. And so if you have a tension in this, then by balance of forces, that determines uniquely the tension in the 3 neighboring double cone elements. And if you apply that at every point in the structure, basically if you know the tension in one of these, you know the tension throughout the structure, and you know the stress throughout the structure as well. One application of this was making a sort of unfillability cloak, where they took this pentamode structure and they took a pentamode structure with a slightly smaller bulk modulus, and they used it to hide a rigid inclusion. So have a movie for this too. So again, this is the experiment of Martin Wegner. Whoops. Okay. That's okay, I think it's working now. Yeah. This is just a reference here, this is a pentamode structure without any structure. Here is the obstacle, and it's being loaded vertically from above, and you can see these lines remain almost level, whereas they are deformed by the obstacle. And yeah, so this is with the cloak, and again, this is the yeah, so this is the obstacle, but with the cloak present, the lines remain almost horizontal here, so it does a good job of shielding what's underneath it. And oops. So, oh, I think no, it's fine now. Yep. So actually, as observed by Norris, this pentamodes can actually be used for acoustic cloaking. They can just guide the stress around the object to be cloaked, even for acoustic waves. So a pentamode has an effective elasticity tensor, which is a rank 1 tensor. And then on a macroscopic scale with smoothly varying pentamode structures, you get an elasticity tensor field of this form, and the associated stress form takes this form here. This is somehow analogous to pressure in the material, and so the stress is everywhere proportional to A of x, and of course A of x must be chosen so that the stress has zero divergence. So, in actual fact, so this sort of key feature of pentamodes is that they are uniloadable, and in fact, practically any elastic web under tension can be replaced by a uniloadable structure. So, if you take something like a bicycle, you've got all the spokes around the rim of the bicycle, and if one gets loose, you have to tighten it. If several get loose, you've got to tighten them one at a time. Wouldn't it be beautiful if you could have webs where you just tighten one of those cable webs, you just tighten one, and the tension in the whole structure was exactly as you wanted it. And in fact, you can do that. And the idea is that if you've got a cable web where more than 4 cables meet, you can replace it by a web where at each junction only 4 meet. And this is sort of an argument by induction. So here I've got a problem where at this junction here, we've got 6 cables meeting, all under tension. And so the idea is to superimpose upon this some tensegrity structure where this is under tension, and this, in the absence of the cables, this would be under compression. When you superimpose them, you end up with a structure where one of these cables disappears. So at first sight, you think, well, this is much more worse, is that so at these points here, I've still got 5 cables meeting. But you realize that when one of the cables goes straight through like this, you can replace it by a structure like this. And again, at most 4 cables meet at any point. And so you can apply this inductively at any node throughout the cable network and replace it by a network which is cable network which is uniloadable, provided it's connected. So I should say that in the early 2000s there was a lot of excitement in metamaterials due to promise of negative refraction. And if you just take a look at Maxwell's equation in a homogeneous medium for the wave equations for the electric field, you notice that you've got this factor of epsilon mu. If they're both positive, then that generates normal waves. But this leads to the possibility that epsilon and mu could both be negative. They should have a small imaginary part from a physical standpoint. But again, then one would get propagating waves as well. And then you actually find out that the refractive index, which is a square root here, takes the opposite sign for the propagating waves. And if you could have negative refraction, this is a simulation of Otto and Hess, and this is a normal refraction of a straw, and this is what negative refraction would look like. This is just a computer simulation. There's a lot of experimental work. In particular, I mentioned the work of Valentin et al. For negative refraction at optical frequencies. So this is the results at different wavelengths, and this line here is 0 for refractive index, and the beam actually gets negative values as the refractive index. And but actually, John Willis here, if the only interest is getting negative refraction, you can actually get that through a layered material with the layers orthogonal to the interface. It behaves a little bit like a diffraction grating. But the part of the excitement with getting this negative refractive index was John Pendry in 2000 had a paper where he asserted that so-called superlens would be able to beat the Abbe diffraction limit and focus finer than the wavelength of light. And so this is the setup. One has a slab with epsilon and mu -1, perhaps with a small imaginary part, and on the surrounding material you have air with a refractive index of 1. And if you have negative refraction, and this was realized by Veselago, if you had a ray hit it striking this interface, it would be reflected back here. It would converge at these two places here and here, and so form an image here. But people quickly realized that actually this is not actually a good solution at all, because this and detailed analysis shows that if you've got a solution here, if you reflect it, you get the solution there, and you've reflected again, you get the solution there. And so if this is a source here, this should be a sink of energy, and this should be another source of energy too. But unless you place a physical source there, that can't be the case. And so the actual explanation of how superlenses work actually goes back to an earlier paper of us that we were considering the we had here we had epsilon equals -1 plus I delta, and here we had epsilon equals 1. And what we actually found, and the equation we had was a quasi-static equation, 0 or source. What we actually found, it was sort of analysis that no matter what the surrounding field was, that in the limit as delta goes to 0, that this should be equivalent to, respond equivalently to a solid sphere of dielectric constant epsilon c. So if I have this in some body, this is meant to be the same body, that these two would be actually equivalent to one another. And this electrostatics problem here, if you recall the method of images, if you've got a source term outside here, there's actually an image charge here, and or this is a dipole, this is the image dipole, and the field outside here is exactly that due to the image dipole plus the actual source. So if these are equivalent, you end up with a source out in the matrix, which seems like a contradiction. And but what we actually found out is that there's large oscillation as delta goes to 0. There's large oscillations in the field which develop in here, and outside this region, it converges exactly to what you'd expect as if there's a source there, and that's something we call the ghost source later. And this is so this is the some simulations showing that. This is a dipole source here, and this is the region of anomalous resonance where the fields get crazy. Outside this converges to a smooth field. So note that there's no discontinuity in the medium in this region at all. And then when the shell was hollow, we found out it was the one of the most striking things, though, we found this sort of effective cloaking, that here we had polarizable dipoles, and as they approach this, sorry. So this dashed line is not a physical boundary at all, but when the polarizable dipoles pass within there, they become cloaked from the outside. And this is the case where you have 7 polarizable dipoles, but the result holds true for any number of polarizable dipoles or any sources producing finite power. And for the perfect rings, the story is more or less similar. One sees these regions of anomalous resonance, and in fact, instead of getting perfect transmission, sometimes the transmission is actually 0, that the lens cloaks the dipole source if it's close enough to the lens. And now I want to switch gear a little bit and return back to elastodynamics. If you just make a comparison between Maxwell's equation, here E is the electric field, and continuum elastodynamics, here U is the displacement field, rho is the density, C is the elasticity tensor. Here you've got a tensor C, which is, as opposed to the elasticity tensor, is anti-symmetric in the first and second pair of indices here. EIJM is the Levi-Civita tensor taking values plus or minus 1, depending if this is odd or even permutation. So when you write them this way, they look very similar, and that actually suggests that the dielectric constant as a function of frequency and the density as a function of frequency may have similar properties. And in fact, there's a close connection between negative density, negative effective density, and negative magnetic permeability. This is a split ring structure of David Smith, giving a negative magnetic permeability. And as observed by Movchan and Ganot, of course, the Helmholtz equation describes both antiplane elastodynamics and TE or TM electrodynamics. And so you can use the same structure to basically give you a negative density for antiplane vibrations. If you vibrate this back and forth, you will get a negative density. And So there was actually experiments in 2000 by the group of Ping Sheng exhibiting negative density, negative effective density, and 2003 they actually understood what was happening. But basically, if you've got a material like this is a rigid body, this is rubber around here, these are lead balls. If you oscillate this back and forth, then above the resonant frequency, the lead will actually be going this direction, whereas the surrounding matrix here will have a velocity going in that direction. So the relation between the physical velocity, which is all you measure from the outside, and the momentum of the lead, which is the heaviest component, they're in opposite directions. So you've basically got a negative effective density in these materials. And mathematically, there was a paper of Zhikov and Bouchitte, Pierre, and Feldbach that explained this. And basically, it's high contrast homogenization, that as the period size goes to 0 in homogenization, you should also let the contrast ratio between the components go to infinity. And this is a one-dimensional simplified model which has this, and you get an expression for the effective mass, which is this term here, and this could have either sign depending upon what the frequency is. And it should be pointed out that this is, in these models, the displacement must be small compared to the cell size. And so this is really only for small vibrations. And there's even earlier work of Ornella and Mattei in 1985. This is the French version. In English, talks about effective density of tensorial character and also of negative densities, actually. And this is a model that you can have of actually sort of anisotropic density here. Different spring constants in the different directions give rise to different densities. And so you can sort of think of it this way, is that in materials with microstructure, instead of having F equals ma, macroscopically, you need to replace this by the force at a given time, depends upon the acceleration at previous times with some sort of interkernel. And that makes physical sense because it takes a while for the internal masses to respond to the applied force. So I guess with the problems with the movies, I was a bit out of time, so I just want to talk about whoops. Yeah, so a different type of microstructure. This is basic. So this is from Korea, but this is a shop that it conveys the idea of space-time architecture. And so this is where one has material moduli that vary not only in space, but also in time. And so this is the, say, the wave equation. And the idea is now we have coefficient A and B that depend both on space and time. And for simplicity, I'm taking space as one-dimensional and of course time as one-dimensional. And so there's actually, this has been studied by Constantin Luria. He's got a whole book about it. And there's a lot of interesting things that sort of happen here. And it's a very active area at the moment. Just mention that if you've got a space interface, such as a glass or something like this, if I've got an incoming ray, then it gets at an interface, remember this is time here, I get a reflected ray and I also get a transmitted ray. And the slopes here have to do with the speeds in the different medium. So you may ask, well, what about if I have a time interface? Well, this is what happens, is that you have a incoming ray, and then you get a ray which is propagated back towards the source, and a ray that continues on. And a dramatic example of this is the experiment of Finkfort and collaborators in Paris. And so here what you have is, so to create an interface, they take a bathtub, and at a particular time they accelerate the bathtub slightly upwards. And so this is, they put it into the water. It's just a bathtub. They put it into the water, this shape of the smiley face. At this particular time here, they dramatically accelerate the bathtub up. So that's like changing gravity in the equations. It creates an interface. And then at a time which is twice the original time, the waves come back to the origin and reform the smiley face. And of course, it's true for the Eiffel Tower as well. They're French, and so that's not surprising. So, so now if we just take, for example, a simple checkerboard. This is studied a lot by Luria, Onofre, Weeks, and co-authors. If you take an initial disturbance here and look at the characteristic lines and how they propagate, to begin with, it doesn't look too bad. But as things go on, you get sort of a real mess for how the characteristic lines develop. And it obviously gets harder and harder to sort of keep track of everything. Probably one needs to use some statistical description. If you want to avoid this complicated cascade, one thing you can do is say, have a zero impedance mismatch, and then you only have a wave or characteristic line going in one direction. And you'd think that would be rather boring, but actually, so this was Luria, Onofre, and Weeks. Actually, what they found is that you get a convergence of characteristic lines, a little bit like a shock, but actually in a linear material. Okay, what we realized is that another thing you can do is to choose the structure to be somehow commensurate with the speed in the material. And so here, c is the speed, and you'll notice that so this rectangle has to be such so that the diagonal is the speed in the material. And so now if you have a disturbance here, when it propagates, it develops into some orderly pattern. And that's what we call this field pattern. And this is an example. If we start the disturbance off at a different point, we develop a different field pattern. So here's another field pattern. So there's a whole family of different field patterns that are generated in this way. And I should emphasize this is joint work with Ornella and Mattei. So here, this is sort of a three-phase checkerboard. This is sort of rather interesting for the following reason, is that you can ask about what happens to the amplitude of the wave as things propagate. And with that three-phase material, you get a new sort of wave. This is space in this direction and time in this direction. You end up with a wave which is excited in the material. So you have your wave front, and then trailing behind your wave front, you actually have an excited wave as well. And if you have a look at the eigenfunctions associated with this, they all have eigenvalues all on the unit disk, which shows that nothing sort of blows up in time. And this is closely related to a subject called PT symmetry, but I don't want to get into the details of that. And this is showing for different parameters, one actually gets sort of a blow up. So this is time in this direction, and this is 10 to the power of 12. So this is a logarithmic scale, so things sort of blow up exponentially. You can, if you know about dispersion diagrams, this shows you the dispersion diagrams for this three-phase checkerboard. And so this is the imaginary part of the frequency and the real part of the frequency. This is where you don't have any blow up. Where you do have blow up, you actually get basically a band gap in space, and so the dispersion relation, actually you get complex values for the frequency, and of course complex values for the frequency means something is blowing exponentially up in time. And anyway, that's thank you for listening. And that's a
let me ask one if I can.
yeah.
So back in the 80s, you mentioned there was a lot of work about bounds. So
Right.
that's about things that cannot be done, if you wish.
Yes.
And in some of these more recent directions, it's fantastic examples of what's achievable. Are there any limits on what's possible?
new bounds or things that's yeah.
In time-dependent materials, for example.
Yeah, I don't know. Yeah, so that's right. I think the area of time-dependent materials is still a lot which is sort of open there, and I'm not aware of any work on bounds in that case. I mean, I guess you could probably get some bound on if you have blow up. I imagine you could get some bound on how quickly it could blow up. But it's sort of rather a subtle question of when you don't get blow up, when you have these propagating waves and things. So, yeah.
Yes.
Was some of this work originally inspired by compensated pendulums?
Oh, compensated pendulums. That's I mean, there is a connection with dynamical systems, but I'm not sure.
They have zero thermal expansion, composed of two positive expansion.
Oh yes, now I understand what you're talking about. Yes, that's right. These, yeah, I mean, you get these alloys, INVAR, for example, which would have sort of close to zero thermal expansion. This is very important in the for gyroscopes. I don't know whether it's still the case, but for a long while it was very important for gyroscopes and things like that. And, but you said pendulum.
I was just thinking if you want a structure which has a constant length when the temperature changes, so you're used to material.
Right. Yeah, this is a little bit different. That's positive and negative giving zero. This shows that you can get positive and positive and get zero.
Positives giving zero.
Yeah. Actually, you need three materials. It's sort of key to have three materials. Two materials is, won't work.
Also, another point, there are negative thermal expansion in some crystalline materials where there are internal rotational degrees of freedom. Are they related in any way to the
I
sort
don't.
of like a centrifugal governor, as it rotates faster, it changes its length.
I see, yeah. Yeah, I don't think there's a relation here. This is basically a static geometry, but there are interesting structures. I mean, there's part of the talk which I left out. Okay, this is sort of a rotating square structure. It has sort of negative Poisson's ratio. But if this structure is sort of vibrating, you can have interesting sort of thermal expansion effects associated with that, and so that that may be connected.
Okay, other questions?